Tools mentioned before that he expressed it's an honor to be here among so many smart people. I will add, I will say the same thing, of course, but it's also an honor for me that you included me in your community in the sense of giving this talk. I see there, of course, many close friends of Frans over very, very many years here, and I'm also honored to be here. I also, with respect to the talk that Han Vink gave before, there will be some overlap, but it will not be completely the same. There will be some technical parts, but not too much, I hope. As Han mentioned, there are relations to the two-way channel I will talk about, and I'll try to focus. I hope what I can give you somewhat is also a perspective on the respect with which Frans and his technical work is held not only here locally, but also worldwide. And I think that's important to mention. Okay, so let me give you a short outline of the talk. It's divided into 4 parts of varying lengths. So first I'd like to talk about Frans, the ideal engineering professor. Then a little bit about his contributions to information theory. So here there's some overlap with Hans' talk. It's a selection of the contributions. I'll talk about, then I'd like to focus on one of his contributions. You saw it already in the title, dependence balance, a best tool for multi-access. And I'll talk about one application recently where I can say to Han, we don't deal just with k equals 2, but we actually can use this tool to deal with many users and even massive systems. And this is what I'd like to give an example of an application of this tool. And finally, some personal thoughts and thanks. So let me begin with Frans, the ideal engineering professor. Some characteristics of this ideal is, of course, first and foremost, a brilliant researcher. Secondly, someone who combines theory with practice. That's, of course, important for an engineering professor. And I would say with a reasonable bias towards the former is also very good to have. And I think you got a feeling of that, or at least I felt I did from the previous talk. He has an insatiable curiosity. You will see that through the wealth of topics that he works on. He's an excellent expositor. That's not the same for all of us, I think. He makes difficult things look very easy. And that's, of course, always a sign of technical brilliance. If you compare to football players, for example, who are really the very top, it looks so easy, right? But then when you try to do it yourself, you quickly realize it's not that easy at all. But I think that's a key characteristic. He's very generous towards students and his colleagues, and modest. In summary, I will say a very Shannon-style researcher. So in terms of the second part of the talk, I'd go through some of his contributions to the information theory topic. First of all, he contributed to very many topics. And I was going through the list of papers. Of course, it's usually easier to do this in the early years because in the later years, things mix up with each other, right? You jump from one topic to the next because it's much easier to do so given the experience. The Prof Schrift, so he did his doctoral degree at KU Leuven under Edward van der Meulen, and of course his name is associated with today as well. The title was already mentioned, where the DMMAC here is a pair of words or pair of acronyms that appears a lot: discrete, memoryless, multiple access channels. Han already mentioned that. I here give just a list of the chapters with technical content. The first one has to do already with this is a Slepian-Wolf theorem, not of the compression type. In fact, it's a channel coding type. So what it is you have a multi-access channel, but you also have a common message that is given to both transmitters. So there's actually, if you do have two terminals again, you have a third message going to both. And this was a key tool in going through the entire thesis. Okay, it was a key idea. The main thing he did, if you look at the Slepian-Wolf paper, it appears from in the mid-70s perhaps. It's not such an easy paper to read. The math is a bit difficult. They introduced a convexification idea that isn't very easy to understand, and it's easy to make mistakes with. And Frans looked at that and showed that it wasn't really necessary to add these things, so he simplified it, made it extremely clear, and that clarity makes it much easier then to apply to other problems, to solve other problems. Chapter 4, I have a special relation to, and I will mention that at the end of the talk, the feedback capacity region of a class of multiple access channels. And you see the other titles there: partial feedback, cribbing, generalized feedback. By the way, a very important result that got popular much later. Han showed the citation list. Well, there were people in the late 90s, early 2000s who took this idea, converted it to the Gaussian channels, basically just took the theory and applied it, and their citation counts are through the roof, right? I mean, there's like 20,000 citations for one or two papers, but really all they did is took Frans's theory and applied it. And of course, it was important to build that link to the wireless communications area, but really the result is Frans's. Okay, and that's why one often has to be very careful in interpreting these citation counts. And of course, for that, one needs to be in the community and to know who are the people who are really doing what then gets a lot of attention. Right. Okay, so one early work he did was this dependence balance result with Andries Hextra, who I think I met early on in my PhD in Veldhoven. So there was the schools of information theory, which Han was, of course, key in bringing to the first formal schools which were held in Europe. I'll say a little bit more about this later. He also got into source coding very early. So there was a paper I found on the computation of the Wiener-Ziv rate distortion function in Fortran. Of course, Fortran at the time, I learned it too when I started my undergraduate studies. He did variable to fixed, fixed to variable, universal source coding, arithmetic coding with Tjalkins. Universal, and a very nice paper from 1989, I will say something about in just a second. So universal compression and repetition times. So my PhD supervisor, Jim Massey, chose this idea, this paper, for his basic information theory course. And there aren't a lot of results from people, researchers in that course. I mean, of course, Shannon and Bob Gallagher's work on error exponents, but he also chose Frans's paper, which to me was a sign of respect for the clarity, simplicity, and depth of the kind of result that Frans created. So this was combined with Elias' representation of the integers and a recency rank calculators, which were developed by another group. The nice properties of this method, which Jim called the Elias Willems source coding algorithm, is that it's universal within a class of stationary sources and ergodic sources. It's asymptotically optimal. It's simple. It's easy to teach and very motivating to students, I think. And it gives you all the ideas you need to understand universal data compression. I show you here one slide. You see on the top right, it says Lecture 13. So this probably was a course I gave at the University of Southern California when I was there in 2009. And what this diagram shows is just an example of this compression. So here we have a discrete stationary source. This one happens to have 3 states and memory 1. Here's the entropy per symbol. Here's the entropy rate. It turns out to be here 1.55 bits. Anyway, the source puts out ternary symbols, 0s, 1s, or 2s in this sequence. Here we're parsing it into pairs. So in the end, the compression algorithm work on pairs of symbols. So there's 9 of them. And what you begin with is a rank. So this is the recency rank calculator. So here the symbols are ranked from 1 to 9. And the way this works is once this first pair comes out, you look at this rank, number 3. That's what you put down here, and then you switch it to 1. So you put it onto the top of the list, and all the numbers up to 3 are then incremented by 1. So 1 goes to 2, 2 goes to 3, and all symbols ranked below stay the same. Then comes out the symbol 2, 2, so you see the number 9, so we put that down here. That becomes 1, and all the other symbols are incremented. Their rank is incremented, and so on. And so here in this for this particular sequence, we get 3, 9, 4, 6, 7, 9, 5, 1. There it is. And then you convert this using Elias's representation of the integers to a string of bits. And of course, it's not too hard to see you can undo this, because it turns out that Elias's representation of the integers is a prefix-free code for the integers. Okay, and that's how you can teach it. It's a lot of fun to teach to students. I mean, I really loved this when I was a student learning this. And it's not too hard using one theorem, Katch's theorem on recurrence times. Frans provided a more general proof in his little paper, but it's not too hard to prove. This is universal for the class of stationary sources. Actually, Jacob Ziv and Aaron Weiner picked up on this, and they did their Lempel-Ziv algorithm and showed it was also universal using basically this method, or the proof that that was found here with some variations. But in any case, I think it's the nicest way to teach students about universal data compression. Yes, speaking of Aaron Weiner, around this time, Frans also did some very interesting work from 1990 together with Aaron Weiner and Jack Wolf, who are both shown there. It's called, the title of the talk, I think it's not a very well-known paper, but it's actually very interesting because it was a very early work on what we today call index coding, but with a more sophisticated model, namely where the symbols are correlated. Okay, so the idea here is they were looking at 3 terminals that see symbols from a correlated source. So there's some joint distribution on these symbols. Each user can then compress the symbols to some number of bits whose rate is Rx, Ry, Rz. These symbols go to a satellite. The satellite takes these symbols and again does a compression and sends it back down to the 3 terminals. And the goal is that all terminals reconstruct all strings. Okay, and they showed using a very clever, they're using the Slepian-Wolf binning, of course, here, and here. So Jack Wolf was involved with that. But it was a very nice method to then also show that, and here are the results. So those of you who are familiar with these first rates, they correspond to the usual Slepian-Wolf compression rate. But what they showed is that what the satellite can send down doesn't have to be the aggregation of all the bits, but I think a little bit surprising, turns out to be just the maximum of these sum rates. So you're basically saving one piece of rate. Very nice paper. They published it in 2002. Why 2002? Because there was a special issue in honor of Aaron Weiner, who unfortunately had passed away in 1997 from cancer. So he was still a relatively young man. I think he was 55 or so, around this age, or maybe 56 or 57. Anyway, I emphasize this because it was a very nice result that was way ahead of its time, and I think doesn't get all that much recognition, as it should. It was already mentioned context tree weighting. So this was the Information Theory Society paper word that was already mentioned. I think Yanis Kontayanis will probably speak in more depth about this, since that's one of his topics. He also worked on, it was mentioned, shaping. So yes, it was much earlier than recently. There's a paper from 1993 I found with Jos on the topic where they show the trellises already. I think it was that paper, I'm not quite sure now, but to do shaped coded modulation, so shell mapping methods and also other methods via trellises. And he picked up on that more recently. And one of the reasons for this is, and I think we've had quite a lot of overlap again and again, my career also started in network information theory. This was something, work that was done by a postdoc of mine, not exactly this, a little bit different style, that was useful for fiber optic communications. And Frans started on that again in 2017, but he basically picked up on an old idea he had already developed and was able to show that these methods were better than the ones that, certainly than we in the group in Munich had been using. The results on data embedding and biometrical identification. So here's the paper with Tanya Ignatenko that was also already mentioned, won the 2011 IEEE Signal Processing Society paper award. And there are many other topics. So MIMO, ARQ, dirty paper coding with real codes, not just the Shannon theory, visible light communications, radar sensing, authentication, and so forth. So a real Renaissance man, someone who is interested in very many topics across for different applications. It was also already mentioned his service to the Information Theory Society as associate editor for Shannon Theory in the Board of Governors, getting the IEEE Fellow recognition. He was then, after that, still served as counselor to the student branch in Eindhoven and chair of the Benelux chapters. Also shows his dedication to young people, I think, which is again, mark of an ideal engineering professor. Getting to the title. So I'd like to now spend the rest of the talk to focus on dependence balance bounds. So here's the paper together with Andries Hekstra. It appeared in 1989. I think most of the work was done around 1984 or 85. That's when he, I guess, joined Eindhoven after his doctoral thesis. He sent me, Frans, thank you, at some point several papers on how that was developed in around 1985, some handwritten notes also, so it's interesting to read through. Now, my focus here won't be on the two-way channel. In fact, it will be on the multiple access channel with feedback. And in the papers from 85, Frans and Andries also were focusing on both at the same time because they realized this method applies to both. So now I'll talk a little bit about technical things, not too difficult, I hope. Certainly the experts, I think, will be able to follow very easily. I hope to give the other persons here an idea of what is going on. So here's the two-user multiple access channel. So the idea here is you have two bit sources. So here's the first message, here's the second message. You have two, let's say, mobile terminals. Have cell phones. They send signals going through a noisy channel, and this is received by, let's say, a base station that's in the corner of the wall somewhere and is trying to recover both of these messages, maybe your emails that you're typing or voice messages, whatever it may be. The most basic model that somehow fits wireless communications is known as the Gaussian multiple access channel, where the channel, every symbol at the output is a sum of these two signals at the input. So there's linear superposition of the electromagnetic waves, plus some noise, which might represent interference from other users or noise generated by the device itself when it's receiving, because you always have some thermal noise that gets in the way. Usually you have some energy constraints on the two transmitters, and then you can show that the capacity region has the following shape. It turns out to be a pentagon shape. This is how fast the first user can transmit. Here's how fast the second user can transmit in terms of rate. And often one always wants to operate on this boundary here. So on this line, what's shown here is just the sum rate, the equal rate maximizing point. But in any case, there's a information theoretic expression for what this line here, that's this bound here. This vertical line here is this bound here, yes, that's this bound here. And this diagonal line is the sum rate bound, right? R1 plus R2 less than mutual information. And evaluating this for Gaussian inputs, we get these nice log of 1 plus signal to noise ratio formulas. Now, going to the feedback issue, so Frans was very interested in feedback already at the beginning of his career. Suppose we now add, communication never is one way with a base station. There's always something coming back. And here the idea is to add feedback that is the best possible. Okay, feedback that you couldn't do better than. It's not necessarily realistic. Why? Because usually here, this is a real or a complex number, and sending back a complex number requires infinite precision. So it's not really realistic, but it's still useful for two reasons. First, it gives you a reasonable understanding of what is possible if you could send back a lot. Secondly, there are some applications for which this becomes more reasonable. If the uplink is slow, when does that happen? Well, for some control applications, like suppose you're trying to control a big plant that can't react very fast, you might have a very fast communication link coming down. So there are some cases where people are interested in using this kind of feedback to understand, let's say, how to control a system. What the interesting question now is, okay, what does feedback give you? What's the best feedback can do? And what Larry Ozerov, who was a PhD student of Bob Gallagher's, later worked at Bell Labs. I had the pleasure of meeting him there as well. What he showed, he wrote a very nice PhD thesis to show that the region is increased, right? It grows to look like this. Turns out to be similar expressions here. The only difference is that x1 and x2, which here had to be statistically independent because you have two encoders that are separated, because you have feedback, you can start to correlate the transmissions. So you can start to correlate the symbols. And the interesting question is, well, how much can you correlate it, and how much should you correlate it? Larry showed that effectively you can coordinate as much as you want for two users. Okay, and we'll see in a second for three that's no longer true, right? So 2 is different than 3 there. In any case, you get this correlation coefficient rho that appears here. And then you see here, if the correlation coefficient rho grows here, then this vertical line starts moving inside, right? It starts becoming less. You're pushing that thing going in. So that sounds bad. Same thing happens here. That goes in. But what's nice here the rho plays a good effect. So that bound moves out. And there's some point that when you start doing this, all three bounds meet, right? And that's what defines this curvy region here, is all the ways of doing that. So basically, Larry Ozerov showed you could get any correlation coefficient effectively, that only those that are important, all the ones that are important, you can achieve. Okay? And what's interesting is now this expression here, and I'll get back to that in just a second. So this bound and this bound, so this plus this turns out to be exactly that, right? That's the point where these bounds meet. Okay, and that will be important to us when we get to the 3-user case. In any case, here I showed you how they did, one way, well, I'm getting ahead of myself. So what Frans and Andries Hekstra did, and it's related to this equality, and I'll show you in a second why. Perhaps I should have put the slide a little bit later. But what they showed is that this point, effectively what they showed is that this point is very special. And you can show this using dependence balance. His bounds help you to show that there's something very special about this point, and it's the following. If you increased the correlation coefficient beyond that value where all three meet, you might think, well, you can achieve that, but it doesn't help you, right? Because the other two bounds move in further, so you get poor rates, but the other bound moves out. But it turns out you can't do that. Okay, and that's not obvious, right? And it wasn't obvious out of Larry Ozerov's work. And the way you can show that this is to develop something called the dependence balance bound. So I took this, I know this long equation, I'm not going to go through it, but the way Andries Hekstra and Frans showed how to prove this is they began with a simple inequality, namely that the mutual information between the two messages given the string of outputs must be positive, because mutual information is always non-negative. And then through a series of steps, they came to a bound that looks like this. I just see now this slide is a bit out of order. I actually wanted to put it after, I think, the next one. But in any case, I'll come back to it maybe in a moment. I'll come back to it in just a second. So the result, if you take their paper by Willems, you can show that this multiple axis channel with feedback is at most the union of rates that look like this. So what you see here is just this extra variable t showing up. I won't want to focus on that, but where this bound holds. So what the theory shows is you can't achieve any correlation coefficient. You can only achieve correlation coefficients for which a bound like this holds. Now let me go back. If you look at this very last line, you'll see here exactly that expression, the mutual information between the two inputs, given the channel output, minus the mutual information between the two inputs without the channel output at that time, right? And if you just rewrite that, you can rewrite that expression like this. And what they did is they interpreted this bound as, I think, a very nice interpretation. It bounds the amount of dependence consumed, namely how correlated the two inputs can be for any transmission, is at most the amount of dependence produced. Here, the amount of dependence that's produced in a picture like that is, of course, based on the channel output. Okay, so that's their interpretation of this inequality, which you can show holds very generally for multiple access channels, as well as two-way channels with a common output, which are intimately related to these channels. Okay, so very nice interpretation. I'd like to give you a different one. Okay, not better, not worse, I hope, but certainly not necessarily better. And what I'd like to say here is that good things are always multifaceted, right? There's not always one way of doing things. There's many ways of looking at those things that are really fundamental. So if I start with this, and this is, I think, the most technical slide, or maybe the next one too, but for those who are experts, maybe you can still follow. Here's the bound, right? Mutual correlation of the transmissions given the output, so consumed, produced. Now, suppose I expand this first expression just using entropies. That's the entropy of the first plus the entropy of the second minus the joint. Similarly with the second one, right, where we just condition on y everywhere. Now just subtract these two. If I take this minus this, I get this mutual information. If I take this minus this, I get this mutual information. If I take this minus this negative, then I get this mutual information. And then we can just add and subtract 0 by adding the terms that we're looking for. And then we'll get, on this side, this plus this is just that. This plus this is also that, so we get it twice. And then we also have those terms appearing. And anyway, very easy steps. You get to this expression. And if you look at that, that should hopefully remind you of this one, just with an inequality. Okay? Now, what does that mean? Well, that turns out to be a submodularity constraint. It tells you you can never have that happen, that this bound isn't active. What it says is all three bounds must be active, irrespective of any coding method you use with the best possible feedback. Okay, so my interpretation of this consumption and production is actually, it's interesting. Feedback somehow has something to do with submodularity. So submodularity seems to me to be quite fundamental in some sense. I don't understand that, but I think it's an interesting way of looking at it. So the bound implies that all three rate bounds are active. So submodularity means if we have a function on sets, so for instance, here's the set function we're going to consider here, the mutual information between the inputs in the set S, and we'll condition on all inputs in the complementary set. Then submodularity means the function, so this mutual information, if we take the union of two sets and add that to the function on the subtraction, on the intersection, is less than the sum of the two individually. So that's submodularity. Okay, and here in this example, of course, the set, we would have function of 1. That's this one here. Here's t is 2, so that's the 2, right? 2 and 1, 1 and 2. And then if we take the union, we get this term, and the intersection is empty, right? So it's a submodularity constraint on the joint distribution of the random variables. Okay, now let's go from 2 to K. It turns out this concept expands to K users, so to more complex multi-access channels. You begin with a similar bound like Hextra Willems did. You just add another message. And what I mean by this triple mutual information is just the sums of the individual entropies minus the joint. If you rewrite this using similar steps as what I showed to you in that long equation, you get to an equation like this. So the joint mutual information is less than a half the double one, so 2 and 1, 2 and 1, 2 and 1. And again, this is a submodularity constraint. In fact, you have many other bounds. You get all the submodularity constraints. That's what you get out of just generalizing what was done there. Here I just write how you can get to this one. I don't think it's quite so obvious. It turns out to be a little tricky. You have to consider sets of this form, and then you have to consider overlapping sets and then play around with it, and then you get to this bound. Okay? Now, what's going to happen for K users is going to be interesting. It turns out that this constraint makes the behavior a little more complex than for 2 users. Namely, for 2 users, I mentioned you may as well look at any correlation coefficient. It turns out here, this bound will limit us to only certain correlation coefficients. And it turns out you can find other correlation coefficients between the 3 users, which would in fact give you better rate regions. But it turns out they're not allowed because the dependence bounds bound tells you they're not allowed. And I'll also want to say that you can actually achieve dependence balance. Okay, so it's a very, very, very fundamental tool. So here, let me now go to the application. So suppose we have a massive Gaussian multi-access channel. So I'm thinking of a situation really with many, many users. So here I have K of them. Same idea, same model, just with more terminals. The Gaussian MAC is the same. We'll look at block power constraints, and it's known that without feedback, the total capacity, you just take the 1/2 log of the sum of the powers plus 1/2 in terms of units per dimension. Here I'm thinking of real dimensions. That's the known capacity region. So if we now add feedback to all the terminals to get a understanding of what's the best you could do with feedback, then it turns out there was a recent paper just from last year that established this capacity if all transmit powers are the same. So it's a young man, Eriksson Sula. He was a student of Michael Gaspar's at EPFL and is now doing a postdoc at MIT with Yuri Polyansky, I think. But in any case, I know he's going to MIT. And for asymmetric powers, even though we don't have a solution there yet, there's an argument given by Joy Thomas of the Cover-Thomas textbook to show that the symmetric case gives you bounds for the asymmetric case. So I mentioned that here too. It's a classic paper from 1987. Okay, now let's go to the defining equations. So it turns out that the sum rate capacity is given by an expression that looks like this. Without feedback, this lambda would be 1. So the lambda is a power gain factor, right? It multiplies P. And this number is 1 or larger. And it's the unique maximal solution of this equation here, of this bound. And this bound is nothing other than a dependence balance bound, namely the one I just showed you before, okay, for K users, all right, which is interesting. It's again a submodularity constraint. And what I'd like to show you now is 2 plots just to show you how this factor behaves, as well as how it's also interesting to study the capacity gain factor. So here we have log of pk lambda plus 1 divided by the capacity without feedback. So if lambda was 1, of course, we get the factor 1. And I'd like to show you how those 2 quantities behave. So here's the first one. So this is the power gain factor versus the total transmit power. The total transmit power in decibels is on the x-axis. The power gain in decibels is on the y-axis. Here's the power gain for 2 users. This is upper bounded by 3 dB because the best that 2 users can do is perfect beamforming, right? And can gain at most 3 decibels of power this way over the basic case, which allows time sharing. That's why 3 dB. As the number of users increases in our system, the gains get larger. And what's interesting is they saturate at some curve, which you can characterize, with equality here. And it turns out you can let k go to infinity, you get a saturation. So for example, if we have, let's say a massive system, 100 users, the idea here is like Internet of Things kind of setup with which also would permit feedback. Let's say the total transmit power is 20 dB for these 100 users, which would mean that every user has a transmit power of 0 dB, right, times 100. Then you can get power gains of around 8 dB through feedback, which is pretty good. Right? That's not bad. That's like reducing the energy levels by a factor of approaching 10. Okay? For low transmit powers, it turns out, total transmit powers, you don't gain very much. Okay, so that's the first thing, and this grows without bound as we increase the total transmit power. Here's the capacity gain factor. Okay, same picture. Here, total transmit power in decibels. Here's the rate gain factor. And this has an interesting form. All these curves is for 2 users, 5, 10, and so forth. They're all unimodal, right? They go up and then they come back down. And what's interesting is that if we go to the very top, we go to the extreme, then the maximum turns out to be a funny number, 1.54 approximately. So maximum capacity gain factor due to feedback is approximately 1.54 when the total transmit power is about 7.3 dB. And what's interesting about that is that improves a basic result of Joy-Thomas, namely, right, so feedback can increase Gaussian MAC capacity by most factor of 1.54. This improves on an old result of Joy-Thomas's, whose title, here's the title of the paper, feedback can at most double Gaussian multiple access channel capacity. And the reason you get this improvement is because of dependence balance. Because what Joy-Thomas used was the cut set bound, which permits any correlation. And the reason you get from 2 to 1.54 is because dependence balance shows that you can't get all correlations. Not only that, this factor is tight. You can show you can achieve it for massive systems. So in other words, dependence balance bound is the fundamental tool to understand feedback for Gaussian multiple access channels. And I'm pretty sure it is for general multiple access channels too, at least in some symmetric senses. In fact, there's still a lot of open ground here. We only have the total capacity. We don't have the whole capacity region. That's the first thing. Secondly, we don't have the capacity for asymmetric powers. And both problems, as far as I can tell, are still completely open. The hard part is finding achievable schemes. And I don't know if dependence balance is the right answer for all points. That's why I said it's a best tool. I don't know if it's the best tool, but at least I know it's a best tool for some points. Okay, so this brings me to my last slide. So what I just showed you on dependence balance was work that was extended. It's a natural result of Frans's clear thinking and especially exposition. And I'm quite sure, and this usually happens for such fundamental results, they always get taken up again. And at some point they become important, and we only realize that later. And so I think it's always worthwhile to recognize these contributions at the time we can. So that's what we are doing today too. On a personal note, and let me say a few words about that chapter 4, I think it was. This is how I got started in information theory. So my start was as follows. I started at ETH. I first was interested in cryptography, so my first project was looking at linear cryptanalysis of block ciphers by Matsui. Matsui had just had a basic paper that appeared around 1991 or 92. I think it was 91, maybe it was 92 summer. So he came back from whichever conference it was, Eurocrypt or Crypto, whatever it was. And so he gave me that paper to look at first. There's a variety of reasons. I then decided, okay, no, I after doing that for a year, I thought, okay, I'd like to get into network information theory. It interested me at the time. So he gave me your paper to read, namely exactly this paper. the feedback capacity region of a class of discrete memberless multiple access channels. And Jim thought the idea of directed information might be interesting to apply to these channels. He was a fan of this. And of course, he was right. And this started me on my own journey through network information theory first, and a few other topics since then. So I'd like to conclude the talk by thanking you, Frans, for your many contributions. And I very much wish you continuing joy with information theory in the years ahead. You mentioned to me just before, it's always amazing once you reach a certain point in your life how fast time has gone by. And I think for everyone who gets older, that is a common experience. But certainly, I think we will benefit very much if we can continue to interact with you and have the pleasure of your many insights and also clarity that you bring to us. So I hope to be able to meet you and interact with you regularly in the future. Thank you very much.